Across millions of miles of high-voltage lines, massive amounts of electrical current are flowing at the speed of light to power your city. The grid functions as a singular, vast machine, a continent-spanning network where millions of components must operate in perfect synchronization across thousands of miles. This system is governed by the N1 contingency rule. It's an engineering standard designed so the network can survive the sudden loss of any single major component, like a power plant or a high-voltage line, and reroute the capacity without a single customer losing power. This safety net is the industry standard, yet single-point failures routinely plunge entire countries into darkness. These massive failures are usually driven by physical events that simply bypass the system's logic, simple physics colliding with high-voltage machinery. The grid's permanence is an illusion. In reality, it is a machine that requires absolute precision to remain stable, where even a minor physical disruption can outsmart our best mathematical safeguards. The 2019 Venezuela blackout was triggered by months of neglected brush pruning near the nation's most critical transmission corridor. During a dry season, that vegetation caught fire directly under the 765 kilovolt lines that transport 80% of the country's power away from the Guri Dam. As the lines overheated and sagged toward the fire, automated protection relays detected the fault and instantly disconnected the lines to prevent the physical cables from melting. This disconnection created an electrical vacuum. Energy from the dam was forced instantaneously onto the remaining parallel lines. Pushed past their thermal limits, these lines tripped offline. The entire electricity highway was severed. The blackout began because a localized safety mechanism functioned exactly as designed. By saving a single line, it initiated the sequence for a nationwide collapse. The power grid is governed by one non-negotiable law. Generation must exactly equal demand every second, or the system begins to fail. When critical transmission corridors are lost, the national grid violently fractures into disconnected zones called islands. In January 2021, an error at Pakistan's Guru switchyard created an unstable power swing and instantly severed the country. The north was left with too much generation, while the south was left with a massive deficit. Chile experienced a similar fracture in 2025 when a software protection malfunction disconnected a 500 kilovolt line. Within 1.6 seconds, the populated Central South region was isolated from its power sources, creating a local grid that could no longer support itself. This isolation is the primary driver of a collapse. When demand inside an island outpaces the remaining generation, the electrical frequency of the entire system enters a rapid, unmanageable freefall. Once the grid separates into these islands, it stops being a unified tool and becomes a collection of fragmented, blind machines. A frequency drop is a physical threat to the hardware. As it falls, massive steel turbines and power plants begin to physically shake and vibrate. During a 2019 Great Britain event, frequency plummeted from a 50 Hz baseline to 48.8 Hz in 16 seconds. To save the turbines, automated relays disconnect generators from the dying grid. This drains more power, dropping the frequency faster and triggering a cascading feedback loop. In these final seconds, control rooms lose visibility, state estimators go blind, alarms overlap, and automated systems execute a cascading nationwide shutdown. It is a systemic contradiction. The very automated safety systems designed to protect the equipment are often the final force that shuts down the entire network. The immediate aftermath is a total disconnection from modern life. Subways stop in their tunnels, and hospitals are forced to rely on finite backup power for life support. Restoring the system is an intensive engineering challenge. Operators must perform a black start, jump-starting the grid from zero without any external power, and carefully resynchronizing every plant and substation across the country. In Pakistan's 2021 blackout, the lack of modern visibility and black start facilities reduced top engineers to blind trial and error. It took 20 hours to restore power to the nation. The cascade that kills the lights is often the result of decisions made months or years before the first relay trips. These failures trace back to human management, the engineering brain drain and unpruned vegetation in Venezuela, the operational negligence in Pakistan, and overlooked software errors in Chile. The physics of the grid are uncompromising. When infrastructure is neglected or technical expertise is lost, a blackout is the inevitable result of those laws being enforced.